In this video, we'll take a look at how we can process signals using the SciPy library. And from the SciPy library, we'll import two submodules. First the signal and then the ND image. The signal submodule offers us functions that we can use for filtering or analyzing any kind of signal. So for example, it allows us to perform convolutions or filter certain frequencies. The ND image submodule provides us with functions for multidimensional images. A classical example from this submodule would be the Gaussian filter or things like edge detection. And with the Gaussian filter, we're also starting here. So in this cell, we have some noisy data and we're trying to reconstruct the original signal by filtering out that noise. And so our original signal is this Y here, which takes X as an input. And of course, since we're in programming, we have to be discrete. So we define X as values between -10 and 10. And how many values we have, we specify with S-rate and duration. So S-rate stands for sampling rate, telling us how many samples we take per second. And in this case, we have 1024. And then we're sampling or recording for 30 seconds. And the product of that gives us then the number of data points that we have. And so these X's we then use to calculate our Y's. And this gives us then this blue graph here, so the original signal. And to that, we're adding noise. And the noise is taken from a normal distribution that we scale with a strength of 1000. And the scaling essentially changes the standard deviation of our normal distribution. And so what it then looks like to add this noise to our Y, we can see in this graph here. So we can still somewhat recognize the underlying signal, but now we also have a lot of noise added to that. Okay, now how do we get rid of this noise? In here we're using two approaches. First the Gaussian filter and then a Butterworth filter. And they work quite differently. So what the Gaussian filter does is that it looks at the neighborhood of one data point and then takes the average of that. And how many neighbors we consider depends on this sigma here. And the sigma stands for the standard deviation of our Gaussian distribution. And so when we are averaging the neighbors, we're actually calculating a weighted average. And the weights for each neighbor depend on this Gaussian distribution. So what that then means is that closer neighbors are considered as more important and further neighbors are considered less important in this weighted average. And what this then does is that it smooths out our noise. And to give some intuition for that, the noise that we add to our signal is centered around 0, so it can be positive or negative. And since the values are random, if we add enough of them together, they will cancel out around 0. And so that's what we can see here when we applied the Gaussian filter. So we're not just considering one data point where the noise would lead to a great offset, but we're considering many data points, and so the noise of these data points cancels out. Okay, next up is the Butterworth filter. And the syntax here is a bit different because we're not just calling butter filter or something, but we're first creating the filter in here and then we're passing it to the SOS fills together with our signal. And what the Butterworth filter does is that it cuts off frequencies. But it's not actually really cutting, but it's more fading them out. And so in this second argument here, we can specify at which frequency this fading out should start. And the 2 in front here tells us how strong this fading out should be. So this filter will then fade out frequencies that are higher than 0.3. And this will then restore our original signal because as we can see, the original signal has a very low frequency and the noise has a very high frequency. And we also have to specify the sample rate of our signal so that this threshold frequency makes sense. And once we have defined the filter, we can pass it to the SOS fills together with the signal, and that gives us then this green line here, which is also an okay approximation of our original signal. Okay, next up are audio signals. And here we have a signal that's a recording of the words 1, 2, 3. And one very common function of audio analysis is the spectrogram. And when we apply the spectrogram function to an audio signal, that will tell us the intensity of every frequency over time. And this information is represented as an image. So on the x-axis we have again duration, same as in our original audio signal, but then on y we have the different frequencies. And in color we can then see the intensity of every frequency for every time step. And so we can see here there are a lot of low frequencies, but also some higher frequencies. And to create this spectrogram, we can simply call the signal.spectrogram, pass to that our audio signal, and again the sampling rate. And this gives us then the frequencies that are tracked, the time steps, and the actual image, so the spectrogram. Okay, finally, image signals. And as teased in the beginning, two very common functions that we can apply to images are a Gaussian blur and edge detection. So to apply a Gaussian blur, we can simply call the ndImage.Gaussian filter. We pass to that our image and again the standard deviation. So how much of the neighborhood should be considered when we do our averaging or blurring. And then the function that we have not seen yet is the previd function. And this is an approximation of the first derivative of an image. Now, what does first derivative mean? The first derivative of an image gives us information about how it changes. so how color or brightness change from one pixel to another. And if we go from black to black, white to white, or from some gray to some gray, then the derivative will be 0 or very low, and so also the resulting value will be very low. And what this then essentially does is edge detection. So if there's an edge like here, so the brightness is changing, then this will result in a high value in this representation here. And now the interesting thing is that the Butterworth filter and the Gaussian filter work very well in combination. So here we can see we pass to the Butterworth filter not just our image, but we first blur the image. And so if we set the standard deviation to 0, so no blurring, then we can see that the edges are not that clean. And that's not because there are no edges, but there are just so many. So looking at this fur here, the pixel values change very often. And so the result then looks very noisy. But if we apply a Gaussian filter, then we're smoothing out these small changes and we're only keeping the big edges, which can be a lot more useful.